Welcome to the lecture video. In this video, I am going to do the tutorial that is content beyond the syllabus. I am not going to explain the problems but only the applications of Fourier transforms and then successive transforms in various different fields. So what are the applications we study here is a novel quantum circuit that calculates the Fourier transform in a much quicker, versatile and a more efficient way. So this is the fast Fourier transform, the application which has been illustrated. So it has many applications. Mainly, it converts the time domain signal to the frequency domain signal, at which signals can be analyzed. Unlike the Laplace transform, Fourier transform doesn't have a full S plane. It just have a frequency plane only. So it helps to analyze the spectrum of signals, helps to find the response of LTI systems. Continuous time Fourier transforms is for analog signals and discrete time Fourier transforms is for the discrete signals. So, discrete Fourier transforms are helpful in the digital signal processing for making convolution and many other signal manipulation. Now, let us see the various fields where and all it is applicable. So, the Fourier transform has many applications in different fields. So, in this video, I am going to explain mainly some 4 fields which I am going to explain. In fact, any field of physical science that uses a sinusoidal signals such as engineering, physics, applied mathematics, chemistry will make use of Fourier series and then the Fourier transforms. It is impossible to give the examples of all the areas where the Fourier transform is involved, but here are some of the examples from physics, engineering and signal processing. So, communications, astronomy, geology, optics. So, important we will be giving now. So, communication. In the communication theory, it is usually a voltage and the Fourier theory is essential to understanding how a signal behaves when it passes through the filters, amplifiers and communication channels, because when we do the communication, how it is exactly useful and how the signal will be behaving, all this will be dealt. Even discrete digital communications. Discrete digital means it is not the continuous one. So it will be using the signals as zeros and ones in order to send the information still have frequency contents. This is perhaps the easiest to grasp in the case of trying to send a signal square pulse down a channel. The field of communication spans a range of applications from high-level network management down to sending individual bits down a channel. And it is usually associated with low-level aspects of communication. This is all about the communication. Still many more things are there to discuss, but now I am making it short and then explaining about the communication. Coming to the astronomy, it is not only limited to the communication on this thing. Now in the case of astronomy also we will be using this applications of Fourier transforms. Take for example the field of astronomy. Sometimes it is not possible to get all the information you need from the normal telescope which we use to study, and you need to use radio waves or radar instead of light. These radar signals are treated just like any other ordinary time varying voltage signal and can be processed digitally. For that, we need a Fourier transform. Next, it is not only limited to the fields like astronomy or communication. Even in the case of geology, we will be using the technique of Fourier transform, that is discrete Fourier transform and for fast Fourier transform, like this. So seismic research has always been a common user for the discrete Fourier transform and the fast Fourier transform, that is FFT. If we look at the history of the fast Fourier transform, we'll be finding that one of the original uses of the FFT was to distinguish between the natural seismic events and the nuclear test explosions, because they generate the different frequency spectra. So coming to the optics. So when we coming to the optics, here is some example it's been given. You can look into the optic axis, object exit wave, Fourier transform, then diffraction pattern. Here the bending happens, the diffraction pattern and the Fourier inverse transform, then the image wave. So one simple example applications of the Fourier transform in optics is the diffraction of light. When it passes through the narrow slits, then the ideas represented here can be equally applied to the acoustic, X-ray, microwave, diffraction and any other form of wave diffraction. So these are some applications of optics. There are many more applications we can find in the optics also. Coming to the Z transforms. If we see the main applications of the Z transforms, then we find that it is analysis tool that analyze the whole discrete time signals and systems and their related issues. If we talk the application areas of this transform, wherever it is used, they are digital signal processing, population science and the control theory. So now here is an example, the Z transform applications. Just let me see this one, show you. It shows that a motor and a gear train that we might use in a servo system. Just I'll expand this one. See, this is the motor and this one gear train. The difference equation that describes the plant might be looking like xn is equals to xn plus 1 of a plus 1 and a into xn minus 1, and this is the difference equation which we can describe the plant it will be looking like. So what are the applications we can study here is when we take an application that will be converted to a difference equation and then find the solution of this, which we have already discussed how the difference equation will be solved. Thank you.